Okay, so in the last video, we figured out that there's 16 symmetry operations, and we could group them into for D4d, and that was the first step in deriving the character table, and then we can group them into 7 classes. And the classes we figured out were, well, identity is always its own class. By convention, we put as the first class. And then we had a C4, and a lot of character tables will actually put, this is a little funky one, they'll put the S8 that we found, the S8 class first, just because it's a higher N. And then we could write the 2S8 3 times. We had a C2 that was a C4 twice. And then we had those 4 perpendicular C2s because this was a DND point group, and we have N perpendicular C2s, and any DN point groups, we have 4 perpendicular C2s. And then it was DND, so we also had the 4 dihedral mirror planes. So we have 7 classes. That means we're going to have 7 irreducible representations. We don't know what the vectors are, what the values are for these irreducible representations. So I'm just, as I always do, going to give them arbitrary names right now. Later we'll replace these with Mulliken symbols, but right now I'm just using the Greek letter gamma and calling them gamma sub 1 all the way down to gamma sub 7, just as placeholders. And gamma 1, we always know the first irreducible representation is just going to be the totally symmetric one. It's a freebie, if you will, ones across the board. Now, from here, we need to use our character table rules. And the character table rule that we always like to use next is that the sum of the squares of the dimensionality, that is the character under identity, equals the order of the point group, or the total number of symmetry operations in the point group. Well, we know the total number of symmetry operations is 16. That's 1 plus 2 plus 2 plus 2 plus 1 plus 4 plus 4. And so what that means is that if I write values here, arbitrary values here, I know that 1 squared plus a squared plus b squared plus c squared plus d squared plus e squared, I'm solving for these variables now, plus s squared has to equal 16. I can take advantage of the fact that these characters under E, the dimensionality, have to be integers, whole numbers. They have to be 1, 2, 3, 4, 5. And 90+% of the time, they're going to be 1s and 2s. Unless you get to the really highly symmetric point groups, then you're going to have 3, 4s, and 5s. But those are pretty rare. And so, we can ask ourselves what values would give these results, and there's only one solution to this, and that's to have 4 1s and 3 2s. Because if you do 2 squared plus 2 squared plus 2 squared, that gets you 12, and then you're left with 4 more to reach 16, and that gets you the 1 squares, right? 1 squared plus 1 squared plus 1 squared plus 1 squared is 4. So this really helps us, figure out what to expect when we're going through and solving this. At this point, I like to test various functions. And so the first function I always like to test is z. And so what I mean by that, right, is like what we always do, we have x, y, and z. We're thinking about how does a z vector transform with all these different symmetry operations. And we define our principal rotation axis, or C4 or a S8, as being a rotation along the z-axis. We have to do that. The x and y, we can align kind of however we want, as long as every x, y, and z are perpendicular to one another. We could swap x and y, for example, have left-handed versus right-handed Cartesian coordinate systems. That's fine. But, basically, we have to have the principal rotation axis being defined as long, coincident with our z-axis. So once we have that, then we think, okay, what happens to this S8? What happens when we do an S8 operation, or each of these operations, I should start off with, to the z-vector? Well, if we do an identity to the z-vector, we go to identity. And then we're asking ourselves, what matrix describes this transformation? It's a 1-by-1 matrix that takes z to z. We take the trace of that matrix, and I always use chi, the sum across the diagonals, chi just to represent trace or character. The trace or character of this matrix, why it's called character tables, for the identity operation is therefore just equal to 1. So that's why we have a 1 up here. we do the same thing for S8 operation, Z is actually going to go to negative Z. And why is that? Because when we do what is an S8? Remember, an S8 is equal to a C8 followed by a sigma H. When we do an S8, we're doing a 45-degree rotation along the Z-axis. Well, that's not going to change Z vector. We take that Z vector and we spin it along the Z vector, the tail's still pointing up, right? The arrow's still pointing up. So that doesn't change anything. But then we follow that up by using a sigma H, which remember is perpendicular to, defined as being perpendicular to the principal rotation axis. So that Z vector is above the mirror plane, so it's going to get reflected below the mirror plane. So that gets you Z going to negative Z. So you can get the value of -1 in this matrix here, take the sum across the diagonal, and you get the chi of the S8 equals -1. You do the same sort of logic for C4, and C4 Z is going to go to Z. You do a 90-degree rotation, you're rotating along the Z, and the arrow is still pointing up. And I'm going to write the chi business again. When Z goes to Z, you're going to get a value of 1. When Z goes to negative Z, you're going to get a value of -1. Notice that it doesn't matter if we did C4 or C4 3 times. That's the other operation embodied in this 2C4 class. That's the beauty of operations being in the same class. They mathematically will behave the same. So it doesn't matter which one we choose when we're deriving the character table. We're going to do an S8 3 times. S8 3 times in the previous video we discussed was C8 3 times followed by sigma H. And it's going to be very similar to what we got for S8. Z is going to go to negative Z. This C3 8 is just going to be a 135-degree rotation. That's not going to do anything. Across the Z-axis still pointing up. But then we have this reflection by the sigma H. It brings it into the negative itself. So we're going to get a -1 there. And then we have a C2. That's our next class. A C2, this is the C2Z. It's a C4 2 times. And that's a rotation right in the Z plane along the Z, wrapping around the Z axis. So it's going to do nothing to the direction of the arrow. So we get 1, Z going to Z. And then we have the perpendicular C2s. And so we can just define one of these perpendicular C2s to be along the Z axis, around the X axis, sorry, or we choose the Y axis, doesn't really matter. But there's 4 of them. They're not all going to be this way, of course. But that's going to be where one of them is if we define it this way. And so that'll make our life easy. And that now we're doing a rotation, right? But perpendicular to a 180-degree rotation. So this axis, this Z vector is going to bend down to the negative itself. So we're going to get Z going to negative Z. So that's going to get us a character of -1. And then we have a dihedral mirror plane. And the dihedral mirror planes are a little bit different, and they are, however, what you can tell with all of them, right? They bisect the C2s, but what they all do is, if you go back to what we showed in the previous video, is they all contain the Z-axis. They all contain that principal rotation axis, right? They're all in the Z-plane. Well, if a vector is in the Z-plane, if the vector is in a plane, it doesn't do anything. So Z is going to go to Z, and that gets you a value of 1. So by using this function, testing this function of Z, we're able to derive a new irreducible representation. And we can check to make sure things are orthogonal, which is always good when you're deriving these things to test just as a sanity check. It can really help you figure out if you've made a mistake in visualizing one of these operations and how it works. And I oftentimes catch many mistakes this way, so I highly encourage you to do it. And remember how this works is this is another character table rule, is that all of the irreducible representations have to be orthogonal to each other. That is, mathematically, the dot product has to be equal to 0. But this dot product is adjusted for the number of operations. It's sort of weighted for the number of operations in each class. So what you end up having here is, I'm just going to, remember the dot product is just you take each component of the vector and multiply them out. So I'm going to write that out, and I'm going to leave some space for the weighting that I talked about. But, I'm going to have 1 times 1, 1 times negative 1. And then I'm going to have 1 times 1, 1 times negative 1. I'm going to have 1 times 1. And I'm going to have 1 times negative 1. And I'm going to have 1 times 1. This whole thing should equal 0, but then I also have to weight it by the number of symmetry operations in each class. So what I mean by that is, right, there's an imaginary coefficient 1 here because there's one identity operation in the identity class. So we times this by 1. And then there's a 2 here. There's 2 operations in that class. So we times it by 2. 2 there. 2 there. A 1 there. And a 4 and a 4. And so if we sort of simplify all this, this becomes a 1, negative 2, 2, negative 2, 1, 4, and negative 4. And that'll, when we sum all these up, is equal to 0. So the math should always work out this way. And if it doesn't, it means you did something wrong. One of your visualizations on how the z vector transformed was wrong. But all of your operations dotted with one another should be equal to 0. So the next one that we derive, gamma 3, it will be orthogonal with gamma 2 and gamma 1. And we can check that to make sure that we didn't make any mistake. Okay, so the next vector, now that we did z, you might as well do x. That's a good one to do next. So let's erase this visualization here. And now we're visualizing an x vector. Okay, and so we're going to ask ourselves the same sort of questions. How does the x vector transform? Well, identity, x goes to x. What about an S8? Okay, well, with an S8, what is that? Remember, the S8 is equal to a C8 times by, followed by a sigma h. Well, sigma h isn't going to be doing really anything because that xy plane is where the sigma h is, and the x vector is in the sigma h. But the C8 is certainly going to do something, and it's going to take that x vector and rotate it 45 degrees. That's the definition of a C8. It's going to go in between x and y. So what this is telling us is that x is actually transforming to some, it's not transforming to y or to x, but some linear combination of x and y. In other words, x cannot be described by itself. It's transforming with y. X must be defined in terms of x and y must be transformed in terms of y and x. And so that tells you back here right away, before we go any more math, we're going to be dimensionality 2. We have to group x and y together. And of course, the identity matrix explains how x goes to x and y goes to y. And then when we take the character with the trace across this matrix, we have a 2 by 2 matrix. We take the sum across the diagonal. And so the chi, the character, the trace of this is 1 plus 1, which is equal to 2, right? The sum across that diagonal. So we can write, we're now actually solving gamma 5, let's call it. And we put x and y together with parentheses to show that they're transforming together. So what does x go into, though, for the S8? Well, it's doing a C8. Remember, we figured out that the sigma h didn't do anything for the x vector. Same thing is true for the y vector because it's in the xy plane, that sigma h. So we need to use the rotation matrix. And we remember the rotation matrix tells us that xy will transform as cosine of theta. In this case, it's 2 pi over 8, which is pi over 4. But so is 2 pi over the n. And we're doing a C8, so n equals 8. So cosine pi over 4, or cosine 2 pi over 8, minus sine 2 pi over 8, depending upon whether or not you're doing clockwise or counterclockwise rotation. You could have a positive value here. Doesn't really matter, as you'll see in a second. But we end up with this. Okay, and cosine 2 pi over cosine pi over 2 pi over 8 is equal to cosine pi over 5, which you may remember is root 2 over 2. And so if you take the trace of this matrix right there, then you're going to get, actually, sorry about that. Let me accidentally delete anything. I'll be back. Okay, I got the key text back. Sorry about that. So, got to make sure I hit the right buttons here. So anyway, we take the trace of this matrix, right? And so chi of S over of S8 is, we just discussed that cosine 2 pi over 8 or cosine 2 pi over 4 equals root 2 over 2. It's going to be root 2 over 2 plus root 2 over 2, which actually just equals root 2. And so quite amazingly, actually the character for under S2S8 class is actually root 2. And so this is not an imaginary character. Some character tables have imaginary characters. This is not an integer character. Okay, it's root 2. So you can have any value you need to have to satisfy the math for characters. Doesn't have to be integers. All right, what about C4? C4 is our next one, right? C4 class, two C4s. We imagine, again, our axes here, and we're doing a C4 now this way, right? And if we're thinking about an x vector, well, that's going to transform x, a 90-degree rotation, into y. And so x is going to go into y. And y is actually going to spin 90 degrees and go into negative x. And so the 2 by 2 matrix that explains this transformation actually has zeros on the diagonal, on the main diagonal, and it's given by 0, 1, negative 1, 0. If you do the matrix multiplication. So you take the trace of this matrix and you get 0 plus 0. And so chi of C4 is equal to 0 plus 0, which equals to 0. So up here you get a big old goose egg, 0. Now, next one is S83. So we're moving right around along. Well, remember in S83, we figured out in the last video, it's just a C83 followed by sigma h 3 times, which is just sigma h. But we already discussed with the SH that the S8 that x and y don't move with sigma h. So sigma h doesn't do anything. So basically we're doing an S8 3 times. So what are we doing? We are doing a, not a 2 pi over 8, but a 6 pi over 8, which is 3 pi over 4, right? Because we're doing 3 times the amount of the rotation we did before. We're doing SA 3 times, not SA once. So 6 pi over 8. So cosine 6 pi over 8, which is 3 pi over 4, cosine 3 pi over 4, and all this same jazz, right, as before, but with 6 pi over 8 now. And so what is cosine 3 pi over 4? Cosine 3 over pi over 4 swings you over to 135 degrees. That on the unit circle, and that's actually negative root 2 over 2. So your S83 chi of that, the character of it, is negative root 2 over 2. I'm going to sum across the diagonals plus another cosine 6 pi over 8, negative root 2 over 2. That's just equal to negative root 2. So here we actually have a negative root 2 as a character. Quite interesting. Now we do a C2, easier one. C2 swings the x-axis all the way around to negative x. Similarly, y is going to swing around 180 degrees all the way to negative y. So x goes to negative x, y goes to negative y, and so xy goes to basically the inversion matrix. And if we take the trace of that matrix, we get -1 plus -1, and that gets us a -2. What about our 4 C2 primes? Well, we defined last time, earlier in the discussion, one of our C2 primes as being coincident with the x-axis. If we have a vector in the x-axis, it's not going to do anything. So x is going to go to x. But check out what's going to happen to the y. The y is going to flip over to -y. And so anytime this happens, your character is going to be equal to 0 because one went to itself and the other went to the negative of self. And so we got a 1. Sorry. Let's just draw this out, getting ahead of myself here and talking. 1 plus -1 is equal to 0. So we get a 0 here. And last one is a sigma d. And so the sigma d is going to be, well, bisecting the C2s. And we know the C2s, if you have a hard time visualizing this, we talked about this earlier here. The C2s are there's 4 of them. So they have to be 90 degrees apart from one another, at least 2 of them do, right? So this C2 and this C2 are 90 degrees apart from one another. And so what's going to end up happening is that if we imagine one of these mirror planes that we dashed out last time is going to go here. And so it's going to go into this axis, okay? It's going to go into this line. If this is the x and this is the y, it's going to go into this line. So this one's a little tricky, but it's essentially x is going to be doing a positive. The x did a 45-degree rotation in this direction. The y is flipping over the other way, right? The y is flipping, y flipped from here, the y vector, and now there's a perpendicular C2 going here. So the y flipped over to this, back to that line. So the y flipped over this way. So in other words, the x got rotated 45 degrees one direction, the y got flipped over with the way we're defining it, 45 degrees the other direction. And so what your matrix is going to look like is, this is for your sigma d, one of your sigma d's. It's going to look like this rotation axis matrix, but your x and y aren't going the same way anymore, okay? Your x went a cosine 2 pi over 8, but your y component went a negative of that. Well, if you have the negative of itself, right, that's going to equal to 0 when you sum this up and you take the chi. And notice I didn't even worry about what these are doing. I could, but I don't even care because they're not on the main diagonal, so they don't contribute to the trace of the matrix. So this is going to end up negating itself out and be a 0. Okay, so at this point, what do we do? Well, I always like looking at other d orbital functions. We did a good job here on this gamma 5. We used x, the x vector, and found that x and y transform together, and that, you know, we derived a new irreducible representation. You could try at this point to use the orthogonality function, but I find that difficult when you're dealing with root 2's. And a clue is that you got some root 2 here under the 2's. Probably these other ones are also going to have, or could have, some root 2's in them. And it's not too terrible working with root 2's. I mean, it's not like you're working with imaginary numbers, which some of the character tables do, or complex numbers. But makes the math a little trickier. So probably the best approach here is to just think about other functions, quadratic functions, d orbital functions that we can use, Right now we did the linear functions, right? X, Y, and Z. So the easiest one is XZ, right? Because, and why did I say this is the easiest one? Because, so just to remind you what the different d orbital quadratics are, they're XZ, YZ, Z squared, X squared minus Y squared, and XY. So we have these to choose from. Let's look at XZ or YZ. You can see that Z times X is XZ, and Y times Z is YZ. So what that tells you is that XZ and YZ have to transform together because X and Y did. And then you just multiply it out. So you go 1 times 2, right? You're doing gamma 2 times gamma 5. 1 times 2 equals 2. Yeah, there's two functions transforming together. But now you have negative 1 times root 2. That gives you negative root 2. 1 times 0 is 0. Negative 1 times negative root 2 is positive root 2. 1 times negative 2 is negative 2. And then you have zeros here, which make this 0. And you can test, and indeed these are all orthogonal to one another. You can test this how we did with gamma 1 and gamma 2. But for the sake of time, I'm not going to do that. So, all right, so we got XZ and YZ. Z squared, you could look at. It's not going to get you a unique function because if you take Z and you square all these values, you're just going to get the totally symmetric representation, which is gamma 1. So that one doesn't actually help you. So let's do XY. Let's talk about XY now. So XY, we're asking the question, how does XY transform under all these operations? Well, for identity, XY transforms as XY. It's obvious. What about S8? Well, we have to now go back and think about what the S8 did. Remember, it was a C8 followed by sigma H, but for both X and Y, it didn't do anything. For the sigma H didn't do anything, so it's effectively just operating like a C8, and it operated like, if we simplify the 2 pi over 8 to pi over 4, right? And sine pi over 4, we had a negative here, and sine pi over 4, we have cosine pi over 4. And so if we really multiply this out, then, well, what is x going to? X is going to root 2 over 2 times x minus root 2 over 2 times y. And y is going to root 2 over 2y, x plus root 2 over 2y. That's what's actually happening. So what does xy go to? It just goes to those things multiplied times each other, right? So it goes to these things multiply one another. Well, now we have a foiling type situation. So let's foil this so we don't have too much text on the screen here. So we're going to FOIL these two terms. So root 2 over 2 times x, or times these two terms, root 2 over 2 times root 2 over 2 equals 2 over 4, which equals 1/2. So we get 1/2 x squared as our first term. Now let's do our last terms here. That's going to look quite similar, but it's going to be a negative 1/2 y squared. And then we're going to have our cross terms. And so our positive cross terms is going to be a plus 1/2 xy. But then we're going to have our other cross term here is going to be a negative 1/2 xy. That's going to cancel each other out. And so interestingly, what happens here is we get that xy is transforming as just 1/2 x squared minus y squared. And that's cluing us in that these are actually going to transform together. You can only describe xy if you also describe x squared minus y squared. So I'm going to write these together here. And I put them down here because if they're transforming together, well, then it has to have a dimension of 2. And maybe hopefully I'm figuring out gamma 7 here, although I don't know that for sure yet. Okay. So how does x squared minus y squared transform? Well, we have to do the same sort of thing, but now we have to square x and we subtract by y. So we have to imagine squaring this term in our head. So again, root 2 over 2x times root 2 over 2x. That part is going to be 1/2 x squared. But now we also have this term squared, which that's going to get us a plus 1/2 y squared. And then we have the cross terms. The cross terms are going to give us 1/4 xy, but it's going to be a negative. So it's a negative 1/4 xy. But then we're going to have that twice, right? Because it's squared. So if we have two negative 1/4, xy is going to get us negative 1/2 xy. That's for the x squared term. Now we take the minus y squared term of this. And so what does that get us? That gets us, if we square this, we will get root 2 over 2 times x squared. Again, that gets us a plus 1/2 x squared. But remember that there's a minus sign here, right? And so we had a minus sign there. And then this is minus y squared. And then we have the same thing for y squared, minus 1/2 y squared. It's this term squared. Then we have the cross terms, which again are going to be 1/4 xy, but we have two of them, and we have a minus. So it's going to get plus 1/2 sorry, it's minus. We have 2/4, right? xy. And so everything is good here, but this is basically going to be this is going to be, so what do? We did this term, we did this term, and now we have the cross terms, and we have a negative of it. It's going to be twice. So we have a minus 1/4 xy, but we have two of those, so it's minus 1/2 xy. And so you can see we have 1/2 x squared minus 1/2 x squared, 1/2 y squared minus 1/2 y squared. Those cancel out. The minus 1/2 xy and the minus 1/2 xy don't. So you get actually just at the end negative xy. And so just like xy, these are now definitely confirming that these functions transform into one another. Xy could only be defined in terms of x squared minus y squared. X squared minus y squared could only be defined negative xy. How would we write a matrix for this to get our character? It'd be a 2x2 matrix, right? And so up here for identity, since we confirm that these go together, it would be the identity matrix. We take the trace across that matrix, and we get a value of 2. And so that's why we have 2 here. For this one, xy goes into actually 0 of itself, but 1/2 of x squared minus y squared, and x squared minus y squared goes into 0 of itself on the main diagonal, but -1. That's how the matrix multiplication would work. When we take the sum across the diagonal, we get 0 for the character. So our character under S8 is equal to 0. Okay? And so now we do the same thing for C4. Okay, so this is quite the laborious process here. For C4, it's a little bit simpler. We know that it's just actually the same thing as this. Because this it's a little, well, not quite. It's 2 pi over 4, right? And so, well, let's just go through it. The easiest way is to go through it, right? So x, remember for C4 went to y, because x goes 90 degrees, and y went to minus x. And so what does xy therefore go to? Xy therefore goes to, well, y times minus x, which equals negative xy. What does x squared minus y squared go into? Well, x went into y, so it was y squared. Y went into negative x, so it's minus x squared. So that equals y squared minus x squared, which is equal to the negative of x squared minus y squared. And so we end up getting a matrix here being negative ones on the diagonal, right? Because that's what would explain this transformation mathematically. So we take the trace of that matrix and we get negative 1 plus negative 1. It equals negative 2. And then we do the same thing for an S8 3 times. An S8 3 times ends up being a very similar type of math. And so what ends up happening there is you're going to get a 0. And why is the math very similar? Because it's similar to an S8, but now you're doing an S8 3 times. And so with an S8 3 times, the only thing that changed here is you got some negative signs. And so I'm not going to work through it for the sake of time, but it ends up being quite similar, and you get a 0. And now if we do a C2, 180 degrees, x goes to negative x, C2, and y goes to negative y. And so what does xy go to? Negative x times negative y, which is equal to xy. What does x squared minus y squared go to? Quantity negative x squared minus quantity negative y squared, which is just equal to x squared minus y squared. So they both went into themselves. That's the identity matrix. So we're going to get a 2. C prime. C2 prime. X goes into x. Done this one before. X goes to x and y goes to negative y. Well, if you have that pattern where x goes into x and y goes into negative y, kind of know what's going to happen. But let's write it down here. Xy is going to go to x times negative y, which just equals negative xy. And x squared minus y squared is going to go into x squared minus quantity negative y squared, which is just itself x squared minus y squared. So we have a matrix here where, and then just to save us space, I'm going to reuse one of these areas that we have, but I'm writing about C2 prime here. We're going to have, this is a negative, we're going to have negative 1 and 1 along the diagonal. Take the trace of that matrix, and you're going to get a 0. And then our last one is a sigma d. The sigma d is again a bit hard to visualize, but remember we did this last time, and so the way that we did that was that actually the x was going to go like a regular way, but then the y was going to go into the negative of itself, because the y was going backwards 45 degrees. And so, or another way of thinking about it, if it is going all the way around except not 45. So what would that be? That would be instead of y going that way. But anyway, it's just negative of itself is the way to think about it. So they both went to this same vector. Okay? Is another way to think about it. So that same vector is x going into this vector and y going into that same vector. Okay? And so now if we think about, and so just for the sake of space, I'm really, you know, kind of slumming it here in terms of the writing, but it gets to be a lot of, long algebra. I don't really love boring you with. But what ends up happening here is xy is then this times this. Well, xy then is just itself squared. So you get a term here which is 1/2. So this squared is 1/2 x squared. And then you get this component squared, that's actually a plus. So you get a plus 1/2 y squared. And then you have and that actually is the only thing you really care about. Because you don't even have to do the other part, because that's the only part that's going to give you something in terms of, oh, sorry, actually that's not right. This is the part you don't care about, because this is the part that has to do with x squared minus y squared. The part that you care about is this part, which is the on-axis part, right? So the diagonal part. So √2/2 times x times negative √2/2 times y, those cross terms, that's going to get you negative 1/4 xy, but you have two of them, so you can see negative 1/2 xy. So that's going to be on the diagonal, right? And then the x squared minus y squared, you got, it's the same, it's x squared, okay, which we already did that effectively, because xy was equal to x squared equals this. But then you have minus y squared, and it's the same thing. So you're going to have minus of that. And anyway, if you work throughout all this math out, you end up getting a 0. Now, if you have some of these difficult ones that are mathematically challenging, you might want to just use the orthogonality principle to help you out. And so kind of see this has to be a 0. In fact, these two terms have to be zeros. The way you can do that is just dot it with gamma 1. So if you have a 2 times a 1 times a 1, that gets us a plus 2. Remember, we have to weight it. Okay, this is a 0, so that doesn't contribute anything. Then we have a negative 2, but it's times by 1 and a 2, so it's a negative 4. So I'm at negative 4, and I'm going to get negative 2. And then I have another 0, so that's not going to get anything. And then I have a 2 and a 1 and a 1, so I'm at 0. And the only way I can maintain zeros here, if this one is a 0, is if this one is also 0. Because if I'm stuck at 0, I have to stay at 0. So that's a way, if you have some of these more tricky ones, you could just Sudoku, as I like to call it, Sudoku it out or puzzle it out, right? And that's probably the easiest thing to do for these other gamma 3s, which we now have 1s. And so again, we're looking for patterns here. And so one pattern that you can see is that here you had in gamma 2, 2 negative 1s. And then if you notice, what matters here is these coefficients, right? If we're trying to be orthogonal with gamma 1, we want gamma 1 to be orthogonal with gamma 3, but both these coefficients are 4. So why don't we just copy over gamma 2, this has to be valid, but swap the negative 1 and 1. That has to be valid, right? At least for gamma 1. We can check with gamma 2 and gamma 3, and it ends up being true. And then of course, the gamma 5 and gamma 6, gamma 7, the math is more complicated. But again, if you check that, you're going to get 0. And then the last one is going to be a little harder to see, and so you have to play for it for a while. It ends up transforming as RZ, and so that might be the easiest. You could do Sudoku it out, but it ends up transforming as RZ. And so let me just show you how that works, because I think it's a rotation vector, so it's a little different, and at least you can see how the rotation vectors transform in the symmetry space, or at least one of them. Obviously, Rx or Ry you could do as well, but those are going to transform together, so you're going to get dimensionality of 2, and so things are going to be a lot more complicated. But let's do the RZ. And so to visualize RZ, the way you're going to do it is just visualize this rotation vector that I just drew, or that's already up there. Okay, it's a vector that's wrapping around the z-axis. Okay, I think I have enough space here. And so obviously it's just we treat it the same way as normal. So this is the RZ. RZ identity goes to RZ, so we get a value of 1. What about an S8? Remember, an S8 is equal to C8 followed by sigma H. Okay, sigma H isn't going to do anything. Well, we have to think about this. Is it going to do anything to this? This is a vector that's wrapping around this pole, so it's in the xy plane. So if the sigma H, which it is in the xy plane, you have a vector that's in that plane, does nothing. So sigma H doesn't do anything. What about the C8? The C8, well, that is defined as a 45-degree rotation in the direction of this rotation vector. So it's going to move this head a little bit, 45 degrees over, but it's also going to move the tail, and we're still going to be spinning in the same direction. So that's still RZ. So RZ is still going to go to RZ, and we get a value of 1. C4, very similar. We're going to get a value of 1, but now, right, we spun it a little bit more, 90 degrees, but we're still in that same direction. S8 3 times is also going to get us a value of 1. And so you see we derive something unique because we got 4 positive 1s in a row. As long as we don't get 3 more negative positive 1s, we'll have something unique. That's C8 3 times followed by sigma H. We said the sigma H didn't do anything. And the CH3 again isn't going to do anything. It's just going to rotate it even more. What about the C2 perpendicular? That is going to flip things. You have this rotation vector, and now, head and tail like this. You flip the head and tail. So now your tail's your head and your head's tail. Now you're rotating the opposite way. That's defined as negative z. So RZ went to negative z. You might, but we visualize that wrong actually, because this rotation vector is spinning 180 degrees in the x direction. So it's actually spinning it up, but the head and tail are still going in the same one. That's pretty hard to visualize, I have to admit. A lot of arrows and stuff going. Let's see. Oh, no. We were right before, -1. Head and tail are just spinning. That was right. We skipped, why I confused myself is because we skipped this one, which is +1. It's a C2, right? So it just spun this 180 degrees more, but still in the same rotation. So that one, the regular C2 went Z to Z, RZ to RZ. The one where we do perpendicular, which we defined one of those perpendicular C2s as being an X, flips it. And that makes sense. And then the mirror plane is one of these mirror planes is gonna bisect, right? Any of these mirror planes is gonna bisect. So we have a mirror plane bisecting the tail is looking at the head in the mirror. So that's going to flip things, and RZ is going to go to negative Z, so we have a -1. At this point, we've come up with all the irreducible representations. The only thing we have left remaining is to remove these temporary symbols we had and give Moleken symbols. And our Moleken symbol rules, I have a separate video on that, tell us that if we have a dimensionality of 1, we give it an A or a B. We give it an A if we're symmetric with the principal rotation axis. Principal rotation axis here is technically C4, but all those are 1s. And so the convention here on this sort of weird point group is to use the higher CN, use the highest SN, which is an S8. And so we're going to call the A's if we're symmetric with the SH, and we're going to give it a B if it's anti-symmetric with the SH, a -1. And then we give it a 1 or 2 if we're symmetric or anti-symmetric with the perpendicular C2s. If those exist, they do exist. We have it because we're a D point group. If we're symmetric, we give it a 1. Here we're anti-symmetric, so we're going to give that a 2. Here we're symmetric with C2 prime, so we give it a 1, B1. And here we're anti-symmetric, so we give it a 2. If we have a dimensionality of 2, we give it E's. And there's no real great way to do this when we have 3 E's. And you know, your 1s, 2s, 3s subscript rules don't make any sense here because we have zeros here. So it's a bit arbitrary, but the way that convention states it for the D4d point group happens to be that this is an E1, this is an E2, and this is an E3. As far as I know, that's just convention, and there's no real rule that tells you that this is that, should be that way a priority. Let me know in the comments if I'm wrong about that, but I've never read anything in the literature that states that. But there we are, we derived the complete character table. Here it is. For your enjoyment, you can see these root 2's there, and the negative root 2's, we know where they come from there. It came from those cosine pi over 4's. And then, you know, we didn't talk about the cubic functions, but we could have derived those as well. But we did use these quadratic functions as well as this RZ to help us out on the rest.